Hello everyone, my name is Huma Samin and I'm doing my PhD in computer science from Eastern University, UK. I'm working under the supervision of Dr. Neridan Como. And today I'm going to talk about priority awareness during decision making under uncertainty and the role of runtime models to offer priority aware decision making. First of all, why priority awareness? So let us consider an example of autonomous Internet of Things network, such as a smart home, which is our first case study. So such kind of network is composed of small computing devices that are interconnected to each other to offer the functional goal of transmission or relaying information within the network, along with achieving the non-functional requirements of minimization of energy consumption or improvement in the packet delivery performance under the different environmental factors of link interference and dynamic traffic load. These link interference and dynamic traffic load environmental factors have an effect on the satisfaction of non-functional requirements. For example, higher the link interference, lower will be the packet delivery performance, more traffic load or higher traffic load will lead to more energy consumption for the network. So therefore, the environmental factors actually affect the satisfaction of non-functional requirements and therefore requires the system to make a trade-off between the non-functional requirements based on their priorities for satisfaction. And these priorities or satisfaction priorities depend on the stakeholders' preferences of the non-functional requirements under different situations. For example, under one of the situations, higher priority will be given to the minimization of energy consumption. For example, if there is a high traffic load and we want to maintain the battery levels for these small computing devices or sensors, or in another case, the packet delivery performance will have a higher priority. So it depends on the different environmental situations or contexts. So hence, such kind of systems are required to take priority-aware decisions under uncertain environmental contexts. But the main challenges over here are these, that it is difficult for the requirements engineers to anticipate at design time the changing environmental context and their impact on runtime trade-offs between non-functional requirements. And it also requires continuous tuning and maintenance of the non-functional requirements priorities at runtime. So for this purpose, actually, there is a requirement of a technique that makes use of a model at runtime or the runtime model to represent an abstract, causally connected representation of a system that offers reflective capabilities in terms of the priorities of non-functional requirements and their specific satisfaction levels. So when the system changes, the runtime model should also change and the other way around. A number of techniques exist that offer decision-making under uncertainty, and those approaches actually, there are certain problems with these techniques. That is, mostly they are design time techniques, or if there are some runtime modeling techniques based on probabilistic models such as dynamic decision networks or reinforcement learning techniques such as partially observable Markov decision processes or Markov decision processes. They represent actually the priorities of all the non-functional requirements as a single combined value, and does not actually represent the individual priorities of non-functional requirements. Whereas control theory based techniques, however, they represent the distinct priorities of non-functional requirements but lack the autonomous prioritization of non-functional requirements. So the main problem with the existing runtime modeling techniques for decision-making under uncertainty are that they typically employ the single objective optimization techniques that make use of a single cumulative utility value to represent a combined priority for all the non-functional requirements. And this combined priority for all the non-functional requirements actually hides information about the different impacts of the adaptation actions on the individual non-functional requirements. Also, the impacts of these adaptation actions under uncertainty may change over time during the operation of the system. So the priorities assigned at design time may no longer be valid at runtime due to the unforeseen environmental context. So the main ideas or the principal ideas over here are that the priorities of non-functional requirements should not be modeled as a single combined value. And also the priorities of non-functional requirements should not be considered as static, as they are required to change according to the runtime context. So in order to deal with these two challenges, actually, we propose a technique known as pre-aware, which is a priority-aware self-adaptive architecture for decision-making under uncertainty. And it makes use of multi-reward FormDB++ as a runtime model to offer priority-aware decisions at runtime. So this multi-reward FormDB++ model is used as part of the monitor, analyze, plan, and execute, that is make K loop. And based on the observations from the managed system, which can be the Internet of Things network, that was our first example, based on the observations, for example, link interference or dynamic traffic load. Based on these observations, once those observations are monitored, based on these observations and the current state maintained by the runtime model, this model can plan for the next adaptation action based on the individual priorities of non-functional requirements, and that adaptation action in the form of the tuning of the network link parameters can be applied on this managed system, that is Internet of Things network in this case right now, can be applied on it. So for this purpose, in order to offer priority-aware decisions, our multi-reward FormDB++ model is actually the model which is based on the multi-reward partially observable Markov decision process, which is a multi-objective reinforcement learning technique, and it supports the runtime modeling and reasoning of the distinct priorities of non-functional requirements with the help of a vector valued reward function. As the individual priorities of non-functional requirements are modeled, so therefore it has the capability of studying the explicit impacts of the adaptation actions on the individual distinct NFRs at runtime, and therefore makes the decisions priority aware. To maintain the required non-functional requirement satisfaction levels, it also offers the autonomous tuning of non-functional requirements priorities at runtime. So our multi-reward FormDB++ model is actually, for this model, we have created a mapping from the multi-reward FormDB model, where states are actually represented as combinations of satisfaction levels of non-functional requirements, and the rewards are represented in terms of the priorities of non-functional requirements, are used to represent the priorities of non-functional requirements, and observations are used to represent the monitorables of the non-functional requirements. Monitorables of the environment. So based on the monitored observations that we have and the current state of satisfaction levels of non-functional requirements, an adaptation action is selected based on the individual priorities of non-functional requirements that are represented in the form of a vector valued reward function. Moreover, this technique, this runtime model, also offers the capability of autonomous tuning of non-functional requirement priorities, as we have a vector valued reward function that is a reward for each non-functional requirement. So based on these reward values, a separate expected utility value for each non-functional requirement is computed, and in the end we have a vector valued expected utility value. So based on these separate expected utility values of non-functional requirements, an adaptation action is selected, and these expected utility values that are computed using the reward functions are known as autonomously tuned individual NFR priorities of non-functional requirements. In order to test our approach, we have applied it to two different case studies. One we have already discussed, which is based on the Internet of Things network. Another case study is based on the remote data mirroring network, which is a disaster recovery technique to offer resistance to data loss by replicating data across servers. In this network, actually, the autonomous adaptation is taking place by switching between the two topologies of minimum spanning tree and redundant topology, and balances the satisfaction of three non-functional requirements, that is minimization of operational cost, maximization of reliability, and maximization of performance. The minimization of operational cost is computed using the bandwidth by computing. It's computed using the bandwidth consumption. Maximization of reliability is computed using the by considering the total number of active network links, and maximization of performance is computed by the total time to write data. So we have to optimize satisfaction levels of these non-functional requirements by switching between the two topologies, and these topologies have an impact on the satisfaction levels of different non-functional requirements, such as MST topology supports the satisfaction of minimization of operational cost and maximization of performance, whereas RT topology supports the satisfaction of maximization of reliability and has a negative impact on the satisfaction of the other two non-functional requirements. So to carry out these experiments, we have actually executed it for different simulation runs of a specific simulator known as RDM-Sim, and for the IoT network, we have also considered a well-known simulation environment for the IoT network for a smart campus. So for those different simulation runs, just to give you an example, for example, in RDM case, the decisions are actually priority aware. For example, at a simulation time step 160, the adaptation action of MST is selected based on the expected utility values of individual non-functional requirements, as the expected utility value of minimization of operational cost and maximization of performance is higher than that of the maximization of reliability. So that's why MST is selected. Whereas at time step 163, the expected utility value of the reliability is higher as compared to the minimization of operational cost and maximization of performance. So that's why RT topology, redundant topology, has been selected at that simulation time step. Furthermore, we also wanted to actually assess the quality of the decisions offered by multi-reward POMDP++ model. As the model is based on the multi-reward partially observable markup decision process, so the model actually considers the decision-making agent working in a partially observable environment, and therefore it maintains a belief over the satisfaction state of non-functional requirements at runtime. So in order to assess the quality of decision-making offered by our runtime model, multi-reward POMDP++, we wanted to assess that to what extent those beliefs that are maintained by our runtime model reflect the actual satisfaction state of non-functional requirements. So the question here is, in a multi-objective decision framework offered by POMDPs, on a multi-reward POMDP, how accurate the beliefs are when reflecting the real satisfaction state of the non-functional requirement. And for this purpose, we have used the technique of logistic regression to perform a binary classification in order to assess that when both the network parameters such as bandwidth consumption and the belief satisfaction probability are considered, to what extent do these two values represent the actual satisfaction state? For example, at a specific simulation time step, if the bandwidth consumption is 4050 gigabits per second or something like that, and the belief satisfaction probability for the satisfaction state of non-functional requirement is 0.9. What is actually, to what extent they represent the actual satisfaction state or false, that is the bandwidth consumption is not satisfied. So by applying the logistic regression, for example, for our example sample, we had the bandwidth consumption of 6.29 and we had the satisfaction probability of 0.86. The actual state was false, and we got the predicted state of false, and based on the results of logistic regression, we got that it is 1.00, that is 100% chance of the meaning bandwidth consumption or satisfaction of bandwidth consumption being false. So considering both the bandwidth consumption and satisfaction probability, there are 100% chances of the satisfaction of bandwidth consumption predicted as false. And similarly, it has been applied to test the assess the quality of decision making by assessing the quality or fidelity of the beliefs. Belief satisfaction probability is maintained by the multi-reward form DP++ for all the non-functional requirements. So as a result, we got the different results. For example, for the 500 test samples, meaning for the case of minimization of operational cost, we got actually correct results, meaning almost all of the correct predictions, except there were 9 where the actual satisfaction state was true and it was predicted as false. Whereas for the other non-functional requirements, there were 100%, meaning we got 100% accurate results, and we had the results with a precision of around 90% and a recall of 1. And our results, meaning have given us, meaning it gives us the that meaning it proves that the runtime model that we are using actually is representing true reflections of the actual system that we have. With these kind of meaning evaluations, we get to that conclusion. So in the end, I'd like to conclude that the pre-aware using multi-reward form DP++ offers a priority-aware model to perform decision-making under uncertainty. And the usage of multi-reward form DP++ underpins awareness and reasoning about the distinct priorities of non-functional requirements. It also allows tuning of priorities of the non-functional requirements to match newly found context. We have applied it to 2 different case studies based on remote data mirroring and Internet of Things network. The next steps are that we want to use this multi-reward form DP++ runtime model as a tool to help the requirements engineer for the A priority elicitation of priorities for non-functional requirements to foresee the in order to foresee those different environmental contexts and setting the priorities for those environmental contexts. Plus, as the model maintains a belief over the satisfaction state of non-functional requirements, so it can help us to support or evaluate the quantification of uncertainty using the different techniques such as Bayesian surprises or some other techniques. Also, as our model offers, meaning reflections of the priorities and satisfaction levels of non-functional requirements, so we foresee it as, or we consider it as a digital twin for the actual system, and we would like to explore this area more in future. Thank you so much for your time. Any questions, please feel free to ask.